Problem 9 on assignment 9 is based on number 5 from lesson 4.5 in our textbook. And you can see here that the Unicode department store has decided to enclose an 800 square foot area outside the building for displaying potted plants and flowers. One side will be formed by an exterior wall of the store. Two sides will be constructed of pine boards, and the fourth side will be made of galvanized steel fencing. And you can see that down here in the picture. And then what they tell us is the cost for the different materials to make the wall. So the pine board is $6 per running foot, and the steel fence is $3 per running foot. Our job is to determine the dimensions of the enclosure that will minimize the cost. Okay, so we're going to have to make a cost function. Before we can do that, we need to introduce some variables. So I decided that I would just call the wood side X and the steel side Y. Right? Of course, that means that the measurement, these are linear measurements, the measurement over here is also X. And we're told that the area in here, not the volume, but the area, is 800 square feet. That means that if we were to find the area of this rectangle, X times Y, that would equal 800. This is called a constraint. This is going to help us deal with extra variables. Oh man, I didn't write that where I could fit it on the video there. It's constraint. I tried to spell it right. C-O-N-S-T-R-A-I-N-T. It's in there. This is a constraint. So this is an important equation. In fact, what we usually do is we solve for one of the variables. I'm just going to solve for y right now, and to do that you divide both sides by x. So my constraint is 800 over x. Y equals 800 over x. And this is going to come in handy when we start to make our cost function. Now, you'll notice that the pine board is $6 per running foot, and the steel is $3 per running foot. So if I make a cost function, which I'm going to try and squeeze in here, my cost function is, I have two lengths of wood fence, so I'm going to multiply by 2, and each of them costs $6, and they measure X feet. Plus I'm adding on my one length of steel, which is $3 per foot, so that's 3y. So this is my cost function. Now I'm going to start a blank screen here, and we're going to start to work with that function. But the idea is that we're going to use this constraint in the cost function so that we have a function with one variable. Then we'll take the derivative and do our minimization, because we are trying to find the minimum cost. And in fact, we're trying to find the dimensions x and y that give us the minimum cost. So let's clean up with a blank screen, and then we'll finish this problem off. So I've rewritten the two equations from the last slide. Our constraint is y equals 800 divided by x, and then this function is called the objective function. That's the one that we're going to try and minimize. I am going to try and clean this up a little bit though. So our function c of x actually equals 12x, because 6 times 2 is 12, plus 3y. Now here's the issue. I want to take a derivative of this function, but right now it has an extra variable in there. And we haven't studied how to do calculus derivatives with two variables yet. So what we're going to do is a little trick here. We know that y equals 800 over x, so we're going to put that in place of y right here. And that will give me another version of the cost function. It's still the cost function, but it's just written in a different way. It's going to be 3 times 800 over x. And when we simplify that, we get c of x equals 12x plus 2400 over x. And this is the function that we want to minimize. So we want to find the critical points after we take the derivative. So I drew that line there just so you can see that now I'm going to actually take the derivative of this thing, c prime of x. That derivative is 12, and then you can think of 2400 over x as 2400 x to the negative 1. And then when you use the power rule, that becomes minus 2400 x to the negative 2, which I'm going to write as 2400 over x squared. I'm writing it like this because it's going to be easier for me to solve this algebraically. Okay, so our job will be, to finish this off, we're going to set the derivative equal to 0. 12 minus 2400 over x squared equals 0. I'm going to solve that on the next slide. Let me just point out that one of my critical points we already know is x equals 0 because it makes this derivative undefined. But x equals 0 does not make sense in our problem. I'm going to build a pine fence. It can't have 0 length. So I'm going to cross that one out. And we need to look for the other solution. So on the next slide, we'll solve 12 minus 2400 x squared equals 0. So as I stated, we're trying to set the derivative equal to 0 and solve for x so we can find our critical points. I'm going to run through a little algebra here. I'm going to add the 2400 over x squared to both sides, so I get 12 equals 2400 over x squared. And then I can go ahead and multiply both sides by x squared because I know x doesn't equal 0 because I threw that solution out. And that gives me 12x squared equals 2400. When I divide both sides by 12, I believe that gives me x squared equals the 200. And so that means x is the square root of 200. We only need the positive square root. And when you crank that out on a calculator, it's approximately equal to 14.142. When you're using approximate answers, just put a little kind of a squiggly equal sign there that means approximately equal to. Once you know what x equals, you can plug that value into our y equation. Remember that our y equation was y equals 800 divided by x, so we'll put 14.142 there. And when you divide that, that's approximately equal to 56.57. So we believe that the dimensions that will minimize the cost for our fencing is if we do 14.142 feet of wood and 56.57 feet of steel. I'll try and squeeze that in there. It's not the neatest job that I've done today, but I wanted to get this video out quickly so that people could see how to attack number 9. The strategy is very similar. Basically, the numbers have changed. But this is a good illustration of how we use a constraint to make the objective function easier by eliminating one of the variables. We can only really take a derivative right now if our function has just one variable. Usually it's x. So we eliminated the y and replaced it with a function of x, an expression with an x in it. And then we did our derivative, set equal to 0, and found our critical point. Good luck, and keep me posted on your progress on this problem and also on problem 8, which is another minimization problem. Good luck.